everyone, welcome to BCP Med. In this video, we're going to be talking about dipole-dipole forces, where they come from, their impacts on boiling points, and how the magnitude of the dipole moment influences their strength. Let's go ahead and get started. In order to understand dipole-dipole forces, we really need to first have a good grasp on the electrostatic interaction, because dipole forces are just electric interactions between charged parts of a molecule. As many of you know, point charges with opposite signs, like these shown here, attract one another due to the electric force, whereas like charges would repel. If we were to represent the force for these point charges graphically, we would see that it follows this inverse square pattern, where the magnitude is strongly influenced by the distance. The farther the charges are, the weaker it is. And it's also influenced by the magnitude of the charges involved. Larger charges mean a stronger force. This same force law can be used to understand the attraction and repulsions of molecules, and dipole forces in particular. Now, when we look at a molecular dipole, which can be modeled essentially as two opposite point charges on the end of the stick, we have to consider both attractive and repulsive interactions. A question that always bugged me as a beginner was why the dipole character of a molecule doesn't simply lead to a net cancellation of attractions and repulsions. Shown below, these two mock molecular dipoles have a partially positive and a negative end. There's going to be an obvious attraction between the opposite charges aligned along the midline between the dipoles, the Y negative charge and the X positive charge in the middle. However, there are also two sets of repulsive interactions between the like charges on each molecule, the set of positive charges and the set of negative charges. Which interaction is going to win out? Well, as we saw, the electric force is strongly distance dependent, so the attraction between opposite charges is going to consistently dominate, provided that the molecules are not forced into a bad conformation. What this means for molecular systems writ large is that polar molecules are going to tend to attract one another and cohere more strongly than nonpolar molecules because, given the free ability to rotate, they'll always align in these favorable electrostatic interaction conformations, where opposite charges are placed very close to one another and can dominate compared to any repulsive interactions between like charges. And this is the origin of our dipole-dipole forces for polar molecules. It is important to note that in order for us to even consider dipole-dipole forces, we need to have polar molecules. There cannot be dipole-dipole forces without a net molecular dipole, even if there are polar bonds in the target molecule. For example, if we look at dichloromethane, or carbon dichloride, we can see from its three-dimensional structure not only that it has two polar CCl bonds, with dipole moments shown by the black arrows, but that these bonds sum to give the net molecular dipole shown in red. On the other hand, if we look at carbon tetrachloride, or CCl4, this is not the case. Although all of the CCl bonds are identical and polar, the vector sum ends up canceling in three-dimensional space due to the symmetry of the tetrahedral geometry. This means that carbon tetrachloride is actually 100% non-polar. What this means is that carbon dichloride, or CH2Cl2 on the left, will exhibit dipole-dipole forces, whereas the molecule on the right, CCl4, will not exhibit dipole-dipole forces. Another factor that we want to consider is how the degree of polarity influences dipole force strength. We know from our electrostatic force equation that the strength of the electric force is proportional to the magnitude of the charge. And if we remember our definition of an electric dipole, we know that the dipole moment mu is proportional to the amount of charge being separated. This means a large dipole moment mu should lead to stronger dipole forces, which would manifest as higher boiling points in a target molecule, since IMF strength and boiling point are directly correlated. To see evidence of this prediction, we can look at the boiling points and dipole moments of some hydrogen and period 3 nonmetal compounds. As the nonmetals move towards the right-hand side of the periodic table and increase in electronegativity, the polarity of the bonds should increase to give a larger dipole moment. We also expect, therefore, that as the polarity increases, so will the boiling point, since the dipole force strength should increase. Beginning with silicon hydride, SiH4, we see a nonpolar 0 debye moment and a negative 111.9 degree boiling point. Moving towards phosphine, pH3, we see a polar molecule now at 0.58 debye and a higher boiling point at negative 87.7 degrees Celsius. At hydrogen sulfide, H2S, we see a more polar molecule still at 0.97 debye and again the boiling point increases to -59 degrees. So it appears that indeed the dipole force strength and the boiling point does tend to increase with dipole moment magnitude, right? Dipole moment magnitude is in fact directly correlated with dipole force strength. You may at this point rightly be wondering what on earth is going on with hydrogen chloride, HCl. The polarity increased to the right as we expected, but very strangely, and opposite to what I've just been describing, the boiling point has actually gone down again, and almost 20 degrees Celsius. This is a non-trivial and rather weird case, which I've actually dedicated a whole separate video to, simply because I found it so puzzling when I first saw it as well. But this exception aside, the general trend still holds. Dipole moment magnitude is directly correlated with dipole force strength, and therefore the boiling point of the target compound. At this point, I want to go ahead and look at some practical comparisons of a few molecules where dipole forces are the dominant consideration towards the IMF profile, so that we can get a more nuanced feel for their origins and impacts. First, we have some fluoromethane species, CF4, CHF3, and CH2F2, and we also have some associated data, which tells us that CF4 is nonpolar and has a boiling point of around -127 degrees. On the other hand, CHF3 is strongly polar and has a much higher boiling point. And then CH2F2 again increases the dipole and the boiling point. Now, at a surface level, it's obvious that the dipole moment here correlates very strongly with the boiling point. A stronger dipole means stronger dipole forces and more molecular cohesion, as we've been discussing. But what may seem odd to some is that the number of fluorines and the polarity seem disjointed. Shouldn't more fluorines lead to a more polar molecule? Well, remember, shape matters. For CF4, our geometry is actually perfectly tetrahedral, which leads to a net cancellation of the dipole moment entirely. On the other hand, for CHF3, the molecular shape leads to some cancellation, but leads to a net dipole pointing away from the hydrogen straight down the middle of the three fluorines. Interestingly, the 2-fluorine species, CH2F2, actually has a larger net dipole than the 3-fluorine species due to the geometry, which actually cancels less of the dipole despite having less overall contributors. This just goes to show how important a 3D visualization of a molecular shape is to understanding their behavior, right? This bent orientation of the 2 fluorines actually leads to less cancellation than the 3 fluorines in this sort of triangular arrangement. And so the CH2F2 molecule ends up with a higher dipole moment and a higher boiling point as a result. Finally, I want to throw out the interesting example of nitromethane, which has a nitro functional group that I've drawn here below. The nitro group has a full formal charge on the nitrogen and the oxygen, so unlike most polar molecules, it's not simply partial charges, but full elementary charges that are making up our dipole. This means it's going to have a very large dipole moment, and indeed it does at a whopping 3.46 dBi, which is almost double that of the fluorine species, which we usually think of as extremely polar. In fact, this is also double the dipole moment of water, which is another molecule that we typically consider as very polar. We should then rightfully expect a very high boiling point from nitromethane, and again we're correct, seeing that it has the same boiling point as water, 100 degrees Celsius, despite having no H bonding whatsoever, right? We know that water has such a high boiling point for its size because of H bonding. Nitromethane is a similar size as water. It only has 2 central atoms between the carbon and the nitrogen, and yet it has the same boiling point purely due to dipole-dipole forces. It's pretty impressive. I hope these examples have given you some good insight into the nature of dipole forces and shown you how important it is to use them in your consideration of molecular properties on the whole. And so with that, we've reached the end of the content for this video. Thank you guys for watching, and if you enjoyed what you saw, please like and subscribe to the channel. Also, make sure to check out our other videos on the chemistry playlist to learn more, and if you're looking to branch out, check out our other science playlists. See you next time!